Algebra 2 honor students, this is going to be Unit 11, Day 5. We're just about at the end of the unit here. And today we're going to extend the idea of exponential applications just a little bit further and talk about equivalent rates. So the whole idea with equivalent rates and kind of manipulating percentages and rates of growth and decay is that sometimes you might be given, for example, a yearly rate of growth. Or, if you think back to, let's say, mortgage payments, or if you think back to interest in a bank account. But you might want to determine based on what that yearly rate of growth is, maybe what your monthly rate of growth is, because maybe you get statements monthly or you're making payments monthly. So ways that we can kind of manipulate an expression to be able to determine what the monthly rate is as compared to the yearly rate, or vice versa. Maybe you know a smaller amount, maybe you know a weekly rate, and you want to determine what the yearly rate is. So all different things that we can kind of change around and manipulate to get a percent that we're looking for here. To start the discussion here, you'll see a bunch of exponential equations up at the top here. It says determine whether it represents growth or decay, and then determine the percent change round to the nearest percent. So if you look at this first example, 3 to the negative 4x, it appears that this is going to be an example of growth just because the base of the exponential is 3. But what I'm going to have us do is for this first example, I'm going to kind of suck in that negative 4 as an exponent with that base 3. And I'll have you think about why we're allowed to write it in this format. Well, a power to a power would mean multiply those exponents, and then we get back to where we just were a moment ago. But instead of expressing it as 3 to the negative 4x, if I write it in this fashion, 3 to the negative 4th, I know is 1 over 3 to the 4th. And 3 to the 4th is 1 over 81. So this is 1 over 81 to the x power. So now that I have it written in that format, now that I see the base is something that's less than 1, I'm definitely thinking this is decay. To figure out the percent that we're decreasing by, well, here's the decimal on the inside, 0.01. So that's kind of a fun one, 0.012345 All right, so we get y equals 0.01234 ... to the x. So what happens is as I plug in values for x here, in each case, you're going to only be left with 1% of what you initially started with. So if you only left with 1%, how much decreased? Well, we decreased by about 99% then is the idea here. Keep in mind that this number in the parentheses is what 1 minus r is equal to. So if you wind up subtracting 1 over and then dividing out the negative in front of the r, you're going to get that the rate is 0.98765 ... So if this is the rate of decrease, it says round to the nearest percent. Well, this would be 98.7%, or in other words, this is a 99% decay rate. You're basically left with just about nothing as you plug in values for x. Now, x could be time in weeks, months, years, days even, right? We're not sure what exactly the value of x is here, but we're just trying to figure out, is this a rate of growth? Is it a rate of decay as we plug in values for x? And it's a very large rate of decay. If we take a look at the next example, it says 14 times 0.35 to the 3rd power. So I'm going to do something very similar here. I'm going to kind of suck in the exponent of 3, like just suck it right into there. And then this is an equivalent expression because if I multiply those, I'm going to get back to where I was. But what is 0.35 cubed? Well, 0.35 cubed on the inside is 0.042875. So we can rewrite this as 0.042875. And again, as time goes on, each time I'm only left with 4% of what I had in the prior case. So basically, if you subtract 1 out of this, it's going to tell you it's a negative number, but the rate of decay in this case is 0.957125. Okay, you'd really divide that by -1 to get the true rate, but if this is the rate of decrease, the rate is approximately 95.7%, so it's a 96% decay rate according to the fact that, over time we're definitely going to be decreasing the initial amount. All right, so try this one on your own. See if you can do number 3. But I'm going to do number 4 real quick with you. The idea here is 14 times 1.5 to the x over 6.2. So when I go ahead and suck in an exponent this time and squeeze it into the inside, I'm going to leave the 14 on the outside. it would be 1.25 to the, well, the exponent that I'm going to suck in if I'm dividing by 6.2 is 1 over 6.2. You just want to make sure that whatever exponent you pull into account with this base here, then if I multiply these exponents together again, that I'm going to get x over 6.2, and that seems like the case here. All right, I like the base of 1.25 as growth. Hopefully raising it to that exponent would also make this stay exponential growth here. Let's see. So if we do 1.25 to the 1 over 6.2, we get 1.0366 dot, dot, dot. Okay. So that's definitely going to be a rate of increase as time goes on. You know, it's a rate of increase of about 3.6%, right? If you subtract 1 out of there, that's the rate of growth. So the rate of growth is going to be 0.0366 dot, dot, dot. And to the nearest whole percent, there's going to be a 4% growth rate. So I think based on these 3 examples, you should be able to go back and try this one on your own, no problem. And I'll tell you, we are going to skip this example at the bottom of page 19 here. I didn't tell you we were on page 19, but hopefully you found it in the packet. Let's go to page 20. At the very top, the population of a large town in upstate New York has 19,413 people in the year 2015. The population is increasing according to the following model. P equals 19,413.96 to the negative 4t, where P is the population in the town T years after 2015. So this is kind of an important thing to pay attention to, that 2015 is the year T equals 0. And then any year after that, we're going to have to add on to figure out what that population is. Okay. Now, it doesn't look like this population is growing when you see a base initially, just at a really quick glance, of 0.96. 0.96 as a base is less than 1, so we're thinking maybe this is exponential decay. But when we find the equivalent rate by sucking in that negative 4 here, sorry for the sound effects, you're going to find that this rate actually does become a value that's larger than 1. Let's check it out. The above equation can be written in the form P equals 19,413 times x, some base just to the t. Okay, I don't want that negative 4 up there anymore. What is the value of x to the nearest thousandth? So we're going to write the population as 19,413 times 0.96, suck in the negative 4 to the t. And then we'll round that to the thousandths place when I type this in. 0.96 to the negative 4th power is 1.177 is what it would be to the thousandths place. So this is equivalent to P equals 19,413, 1.177 to the t. Now it's definitely a rate of growth as time goes on, okay? And then this one says, if the population growth is compounded annually, what is the rate of growth? So this formula right now, if t is the time in years, this is going to be representative as I plug in t, an annual growth rate. All right, and we want to go to the nearest tenth of a percent. So if you take that number on the inside, 1.177, and subtract 1 out of it, just like we were doing on the front page, you're left with 0.177. So this represents a fairly large growth rate in this town, 17.7% rate of growth for this particular town. And then using the original formula, what was the average rate of change in the population from 2015 to 2020 to the nearest whole number? Use appropriate units to label the answer. Hint, we did average rate of change on unit 3, day 1. Oh boy, we have to go way on back here, all right? But I'm gonna have you try this one. And if you don't remember what average rate of change is and you can't find your notes for unit 3, day 1, and actually might be for us unit 4, day 1. I'm gonna have to check that a little bit. But beyond that, I think that you can probably Google average rate of change real quick and figure it out. What's the average rate of change in the population from 2015 to 2020? Try it. All right, and this is also something we're going to save for class. So I'm really trying to save us a little bit of time today. We might do a lot of this in the recap. We also might wind up skipping over some of these things, but let's go right on to page 21. Okay. So continuation of our discussion here of changing up some rates and how does that affect what the overall equation looks like. We're going to consider an example here where we have a population of rabbits, okay? So in example 1, a population of rabbits is growing at a constant percent rate. The population on January 1st was 1,027, and then a year later it's 1,079. And the question is, what is the rabbits population yearly percent growth rate to the nearest tenth of a percent? All right, so to determine what the population for is the yearly percent rate, let's use the formula that the end amount is the initial times 1 plus a rate to the t. And I'm going to do 1 plus the rate because I can clearly see that the rabbit population is growing. So we know that the end amount is 1,079 when the initial amount was 1,027. And that's when the time is 1 year, right? So a year later, the population is 1,079. So we can really quickly solve this for the rates. 1,027 is going to get divided from both sides. Let's see what that is. Oh, and by the way, 1 plus r to the first is just 1 plus r. That makes this a little bit nicer to solve. 1,079 divided by 1,027 is 1.0506 dot, dot, dot. Okay. So if I subtract the 1 from the other side, we get, of course, 0.0506 dot, dot, dot. And it says, what's the yearly percent growth rate rounded to the nearest tenth of a percent? So we want to convert this to the tenth of a percent place would be actually the third decimal place, right? So this would be 0.051, which is a 5.1% growth rate. Okay. So from there, what we want to be able to do is write a function that models the rabbit population in terms of t years since the study began. Okay, so if the rate of growth is 5.1%, I can come back to the original equation and say y equals the initial amount of 1,027, and then 1 plus this rate, we actually had it up here already, is 1.05, I'll stop at the 1 this time, to the t. So now for any given number of years later, we can go ahead and calculate what the rabbit population is in any given year. Okay. We're going to extend this out a little bit further, though, and think about some of those equivalent rate ideas that we were just working with a moment ago on the other page. So it says, now let's try to determine what the percent growth rate in the rabbit population would be over a decade of time. Decade, of course, being 10 years. We will assume that the rounded percent increase found above continues for the next decade. So if this pattern continues for another decade, what percent growth will we see over the course of those 10 years? Okay, so the question says, after 10 years, what will we have multiplied the original population by, rounded to the nearest hundredth? So I'm going to plug in to see what happens 10 years later. All right, let's see what this new rate is when I raise that to the 10th power. So it's going to be 1,027 times something. Let's see. 1.051 to the 10th power is 1.6444. Okay. So what will I multiply the original population by rounded to the nearest hundredth? To the nearest hundredth, I guess, would be this place right here. You're multiplying the original population by 1.64. 10 years later, you can see that this is the amount you're multiplying the original population by. So therefore, what is the decade percent growth rate? Well, according to this model, the decade percent growth rate is approximately 64%. Right? It's 64, maybe even a little bit more than that. The yearly growth rate, annually, we're growing by 5.1%, but over the course of 10 years, we're growing by 64%. And notice how that's not just 10 times this rate right here. So we have to raise this rate to the 10th to figure out what that decade percent growth rate is. And then the last piece is we want to say, to write a function that models the rabbit population t years after the study began in terms of the decade percent growth rate. So we still want t to be time in years, but we have to figure out, how am I going to adjust this formula to use this decade growth rate? So I'm going to come back down here, and I know that this number right here is my yearly rate to the 10th power. So what I'm going to do is I'm going to adjust the exponent up here accordingly, such that this would balance out to get back to the original equation. And in order to do that, you're going to raise that to the t over 10 power. If you choose this, this is going to be appropriate for the decade rate. But notice how 1.644 raised to the 1/10th power is the original growth rate, 1.051. So I want you to think about why that makes sense. If this is 1.051 to the 10th power, the 10th and the 1/10 year would cancel each other out to get you back to the annual rate. But we're converting this over to a new formula. Let's say it's more useful for us to think of the rabbit population as in according to a 10-year rate of growth. Here's the 10-year rate of growth percent. T is still time in years. So if you wanted to figure out what the rabbit population is in 3 years, you'd plug in 3 for T there. But notice how T divided by 10 is the number of decades. So when I plug in 10 here, 10 would be 1 decade. Yeah, 10 over 10 is 1 decade of growth. If you were to plug in 20 years later, 20 years, 20 over 10 is 2 decades of growth. So it takes a little while to get used to how do we adjust these exponents to get an equivalent equation to what I started up here in terms of the annual rate. But I promise we'll do a little bit more practice with that and then hopefully start to feel more comfortable with the process. Okay. All right, I'm going to go ahead and skip example 3. We're going to go to example 4. This will be the last one we kind of talk about today. For example 4, we're going to take a look at some llamas. Okay, a population of llamas stranded on a desert island is decreasing. Oh, the llamas, sorry. Due to a food shortage by 6% per year. Sorry, llamas. Given that there are currently 350 llamas, and the number of llamas T years from now can be determined by this formula right here. So 6% rate of decrease makes sense to me that that number is 0.94. We're left with 94% of the llamas as years go on. Right, an expression that models the llama population in T years in terms of a monthly decay rate. It's supposed to be decay, by the way. All right, we want to figure out what this is in terms of a monthly rate. So in order to calculate that, we currently have the model in terms of a yearly rate of 0.94. To go from a year down to a month, what we're going to have to do is we're going to have to raise that to the 1/12th power. Okay. So what this winds up becoming is you're going to get 350 times 0.94 to the 1/12th. But now this is not really time in years. You might want to call that exponent n. This would be representative of the monthly rate. And you would have to plug in a number of months there to account for that. Oh, and by the way, 0.94 to the 1/12th power is, 0.99485. So notice how each month of the rate of decrease is only about like 0.5%. So that by the end of the year, we're accumulating to a total rate of 6%. So this is, let's round it to 0.9949 or something like that. Okay, so we get the population is 350.9949. But again, this is a monthly rate now, so we have to plug in a number of months as the exponent. But the question doesn't say to write it in terms of the number of months. It says write the expression in the number of years. So I want you to think about the balance here. If I wanted to replace this exponent with T, where T is time in years, if I raise that rate on the inside to the 1/12th, what do I have to do to the outside to maintain a balance here? Well, to maintain that balance, if you raise the inside to the 1/12th, the outside of the exponent is going to have to get raised to the 12th. So if you take that monthly growth rate and you raise it to the 12T, the 1/12th and the 12 would cancel each other out, and you would get the original rates to the T, that yearly growth rate. Okay. So now we can do this as T is time in years, because we're using a monthly rate. But when I plug in the number of years here, if I plug in 1 year, that would be 12 months later, right? If I plug in 3 years, the exponent becomes 36. So we would be using the monthly rate for 36 months. So the hardest thing for students to remember is, what do I put on the outside? Is it a whole number? Is it a fraction? Well, if you raise the inside to a fractional power, the outside's a whole number. If you raise the inside to a whole number, the outside is a fraction. And compare that to the last example with our rabbits, right? I raise the inside to a whole number, 10, so the outside is 1/10 T to keep things balanced. Here, if I raise the inside to the 1/12 to shrink it down to a monthly rate, then the outside now becomes 12T. Right, an expression that models the population in terms of a 5-year decay rate. So I kind of like this question because it's going to help me think about, what if I went in the reverse direction? Currently I have a yearly rate. How do I get to a 5-year rate? Well, the population would be 350. Take that annual rate and raise it to the fifth. But then to keep the balance here, we have to raise the outside to the 1/5 t, where t is time in years. So if I plug in 5 years, I'm going to get that 5-year rate. If I simplify just the inside, 350, let's see, 0.94 to the 5th power. Oops, not divided by 0.94 to the 5th is 0.733, so 0.7339. All right, so this is the 5-year decay rate. So if I plug in t as time in years, 5 years later, we would see that the population of the llamas have decreased by about 73% over that time. And then we'll talk about part C in class, where we're going to use the original formula along with the two we've created to predict the number of llamas remaining after 10 years. And they'll all be very close to each other. And they should be, right? If they're off by, hundreds upon hundreds of llamas, that's no good. But we're going to figure out, based on the fact that we're looking at 10 years later, what each of these equations, the original, part A, part B, what they would give us there. All right. I know this is a lot to digest. I promise we'll do more practice with it next time I see you in class. But if you have any questions about what we talked about in the notes today, please make sure you reach out to me next time I see you in class. Have a great day.